In this video, I'll be discussing the setup that you see here in figure 228 from your process control manual. The setup here consists of controlling the pressure inside the column. So from the bottom of the column, there will be water pumped through the pneumatic control valve, and the pressure of the air at the top of the column will be measured with the differential pressure transmitter. So again, what I have water that will be pumped through the pneumatic control valve in the column, and that will create pressure, air pressure at the top of the column, because the top of the column is sealed, and that will build up pressure at the top of the column. I will show you my electrical connection. So this consists of my electrical connection. I have eliminated the recorder to simplify the connection. So what I have is my PLC, so PIC. I have my differential pressure indicator, TDI, and I have the pneumatic control valve. So 3 instruments. Of course, you can include the recorder or remove it. I'm not using the recorder, and that simplifies slightly my connection. This is how my setup looks like. So I am pumping water through the pneumatic control valve in the column. So as you can see here, there's water in the column, and at the top of the column there is pressurized air. So the top of the column is sealed, and I'm measuring pressure with this differential pressure indicator. So I have set a maximum and a minimum as outlined in the experiment. Obviously, the measurement of pressure is done at the top, and ideally I should have my differential pressure indicator over the pressure measurement location. So wherever you're measuring pressure for air, your instrument should be above the measuring point. For liquid, it should be below. But I don't think I could. I can install my indicator at the top on this black pipe that you see. I don't think I have the right to do that. So ideally it should be above, but I don't have any means to do that. So I won't be doing what's ideal, which is to have the instrument above the measuring point. So as I said, this is measuring. In this video, it's measuring pressure of air. So the tank here is sealed at the top. To zero my instrument, I had to remove one of those caps in order for the air inside my column and outside of the column, that will allow the inside of the pressure inside of my column to be equal to the pressure outside of the column by removing one of the caps. So I have one here, and one here. I only need to remove one of them, and this is the one that I have removed. And when I removed it, the pressure inside my column and outside my column were equal, and that's when I zeroed my instrument. When I returned the cap, so of course I had the water level was at 0, or approximately at 0, and then when I started pumping water inside the column, the more the water rose, the higher the pressure was inside the column, and the higher the pressure reading was in here. on the reading on the instrument. This the column itself, it's draining through this valve. So this is valve number 4, hand valve number 4, because otherwise it would be difficult to self-regulate this setup. So it has to be self-regulating in order for me to control it. So what I will do right now is control it automatically using P, and then PI, and then PID. So if I look at the HMI that I have here, so the blue is my set point, which I have set. The green is the process variable, which is the pressure inside the column. So it's the pressure at the top here of the column. So everything over the water level is air, and this is my pressure reading. And my pressure reading right now is 85.90% of the span that I have set up my transmitter to. So that corresponds to approximately 3.953 psi. So we're not far from the maximum. I think the maximum is 4.5, if I'm not mistaken, and the minimum is 0, of course. So so the green here indicates my maximum, 85.87%. So what I'm doing right now is P control. Okay, so you can see here I have P, TI, TD. TI is for the derivative, and TD, so TI is time for derivative, and TD is time for TI is for integral, time for integral, and TD is time for derivative. So again, P is proportional control, TI is for integral, and TD is for derivative. I have set the proportional at 1, and it is enabled. So this is what I am. This is how I'm controlling my setup. I'm controlling it with P. And if you take a look here, there's an offset. There's an offset between my my blue line and my green line, and this makes sense because the disadvantage with proportional control is that you will have an offset. Okay, so there is an offset. You can see it here with the columns. The blue is lower than the green, so the process variable is slightly higher than my set point. You can see that here with the percentages as well. Around 16%, the difference between my process variable and my set point. So my set point is at 70%. So I'd like to make them a little bit closer. And to do that, I will be following the procedure outlined in your manual. And this is the procedure. It's on page 57. That's figure 225. So this is the procedure. So I'm going to start with a low value for my proportional control, and I'm going to make a set point change to see how my system reacts. So I'm going to make a set point change. I'm going to change my set point from 70% to 50%. Of course, you can choose another value. I've decided to use this value instead, 50. Could have made it another value, 40, 30. So I'll take a look at how my system will react. So I don't have any oscillations. It's pretty stable. And if I look at the procedure here, it says that is the process underdamped or oscillatory? If not, then I should increase the gain by twice. And that's what I'm going to do now, because it's fairly stable. If you take a look, it's not really oscillating. Pretty stable. And I do have an offset. Well, the offset is evident if we look at the columns right here. You can look at the graph, but it's a little bit less clear because of, on the camera at least, it's less clear. So there is an offset, it's obvious, between the process variable and the set point. So what I'm going to do, I'm going to change the the proportional control. So I'm going to change the gain from 1 to 2, because that's what your book says. I'm going to do that, but I'm going to have to also change the set point in order to see how it reacts. Okay, so I'm going to change the set point from 50 to 70. Of course, you can choose another value. Take a look. So of course what I'm trying to do is I don't want oscillations, because oscillations is not good for my system. It's going to wear out my system. Anything that oscillates will wear out your system faster than when it's stable. So it looks like that I will again have an offset that's normal with proportional control. And it will just end there, just with an offset. So no oscillations. So if I have no oscillations, again I will increase the proportional gain. So I'll increase it this time, double it, just like what your book says, your manual says. So I'll double it to 4. And then I'll change the set point. Make it 50. So now we can see there are oscillations. Already we can see oscillations. So we need to wait though. Before we draw conclusions, we should just wait a little bit and see if it's oscillating. So here I have put a close-up, and here it's not a close-up, it's the regular view, if you like. So I have a little bit of oscillations. Not too much, but just a little bit. So what I'm going to do, because I want to avoid oscillations, and what I'm going to do is I'm going to do exactly what your book says, is I'm going to reduce this value to half of, bring it in between, that is, the previous value and the current value. The previous value was 2, and the current value is 4. So and the reason why I'm doing this is because there is a little bit of oscillations. You can see here, it's hovering. There is an offset, obviously. We're not at set point. We're going to get to it soon. But so there is a bit of an oscillation. So I'm just going to avoid oscillations. Oscillations are bad, and so at least in this case, so I'm going to reduce it to 3, because the previous value that I had was 2, this current value is 4. So in the middle, I'm just going to go in the middle, and that's 3, and that will be it. So this will be the end of my configuration for the proportional value. So the gain for the proportional control, that is, not proportional value, but the gain for the proportional control. So there is an offset, obviously. We're not at set point anyways, or we're near it, but not at set point. So you can see there's an offset between set point and the process variable. So now what I will do. So notice that that's only the proportional gain that is enabled. The integral ti and derivative are both disabled. The integral value, the initial value, I have set it up to 50. So the value that by default is 20, but I have decided to set it up to 50 because your manual says to put it to the maximum value. I could have put it to a higher value. The maximum value that you can set it up in this system is 99. Maybe a little bit higher, but I couldn't go to 100. So I set it to 50. You could set it to a different value. This, of course, is arbitrary, and it's really up to you how much, what values you want to put in there. Okay. So right now I'm at the stage of enabling the integral. So I'll enable it, and I will make a set point change. So I'll change the set point to see how it reacts, because this will make it more evident. If it's working well, then we should be able to get to the set point. If it's not working, then so you have to change the set point, because otherwise you won't know if your configuration, the values that you put in, are working or not. So this is why I have made a set point change to see if my proportional integral is working or not. Okay, so of course we have to wait a little bit. The process does take time before it reaches the set point, or close to it, or comes to a steady state, whether it's oscillating or whether it reaches a value close to the set point. So we can see now with proportional integral, we're even closer to the set point than when we had only proportional. So proportional integral has allowed us to reach a closer value than the proportional control alone. So we're very close. We're 2.5 approximately % off. So there is no oscillation, and your book says, just go back here, it says that if it's not oscillating or it's not underdamped, then I should decrease the integral time by a factor of 2, and then make another set point change to see if it works. So we're very close. So what I'm going to do, I'm going to divide that value of the integral time by 2. I'm going to make it 25. And then I'm going to make a set point change. So let's see how it reacts. By the way, now the amount that I have opened my hand valve here, if I change it, that may change. If I change it, that may change the disturbance. Okay, well, it will actually change the disturbance of my system, and that may have an impact on my values for P and the integral value that I have put. So if the valve opening changes, I may have to adjust my values for P and for the integral, for the gain, and for the proportional control and the integral control. But I'm not going to do that. Not for this experiment. Maybe in another experiment. So if I take a look here, the value for the set point and the proportional value are very close. They're very, very close. So I have no oscillation or anything like that. So what the book is saying is that if I have no oscillation, then I can decrease it by another 2. Okay, so let's see if I can get a better value by decreasing it by half. So I'm just going to go 13. I'm going to make a set point change because I want to know if these values are going to work or not. It looks like this one is oscillating a little bit. You can already see that it may be. I'm not sure, not absolutely sure. Probably going to oscillate a little bit. It's actually pretty good. It reached the set point. We're at set point right now. So since it's not oscillating, what I'm going to do, we're almost at set point. Very, very close. So what I'm going to do, I'm going to decrease it again by half. It's going to put 7. And I'm going to make a set point change. So this is oscillating a little bit. So I'm gonna go back to the so in between the previous value. So I went down from 50 to 25, from 25 to 12. Well, I put 13, and now I'm at 7. So I'm gonna put it in between 7 and 13. So between 7 and 13, 10. I'll put 10 as a value. So now what I'm going to do is I'm going to kick in the integral, the derivative, that is. Okay. So I'm going to start with 1, smallest value, because derivative you want to start with the smallest value and not the largest value. Okay. Because derivative is sensitive to noise, and any process that has a small period. That is a slow process should have a small process will probably have low noise, not necessarily, but a fast process will change much faster than a slow process like the one that we have. So you want to be conservative with your derivative. You want it to be a small number because it's sensitive to any changes in the process in the air. So you want to start with a small value. I still have not enabled it, but I will enable it in a moment. So I'll start with a small value because it's sensitive, as I said, to air changes. So if the air is changing a lot and you have noise, the derivative is not going to work very well. So my system right now is fairly stable. You can see it's fairly stable. So I can bring in the derivative without worrying about throwing the system off, of making it unstable, that is. So I'm going to enable it right now, and I'm going to change my set point. So I have changed it to 70%. I'm going to wait for the system to react. You can see the green line is joining the blue line. So let's take a look at what the manual says about derivative. So this is a flow chart that is used for programming, but it can be used for a lot of things as well. So is the process response longer and is overshooting amplified? If it is, then increase the derivative. If it's not, then increase the derivative. If it is, then reduce the derivative. So if we take a look at what we have right now with one time derivative, we have a very close value. We're very close, and the system is very stable. The pneumatic control valve is also very stable. It's not working very hard. So what I would like to do is change it to 2 and just to see what I would get. So I now have changed it to 2. I'm going to change the set point just to see what I get. I'm still pretty close. Very close to the set point. I'm going to change it to 3 and see what I get. I'm going to change the set point again. So again here, this is trial and error, by the way. And this is exactly what I'm doing. I'm following what your manual is saying, but there's a bit of trial and error here. So I'm very close to the set point. Of course, I can still fine-tune the derivative. So what I would like to do right now is change the set point and to see how my system will react. And of course, you want to try different. To fine-tune it, you'll have to try a few values for P, a few for TI, a few for TD, but not too far from the ones you already have, because otherwise you may make your system unstable. So this video has already lasted for 33 minutes. What I'm going to do is change the value for my set point. So I'll make it 20%. And watch what it does and see if I'm able to get to the set point in fairly quickly. It looks like it reached the set point. I'm still a little bit away from it. It'll take a little bit of time before I reach it. But I can see it is getting close. And the valve is not working too hard. It's pretty stable. So it looks like we've reached a fairly stable state. So I'm gonna change it now to 40. Change it to 45. Since I don't have any means to make it ask the PLC itself to find out what the values are for P, I, and D, then I actually have to do it myself. So not all PLCs have the ability to find the those values, P, TI, and TD. So you may have to do it for some processes on your own. So it looks like, again, I have been able to reach the set point fairly quickly, and with my system remaining stable. So I'll change again the set point. I'll make it 80, 80. You can see the green line is slowly reaching the blue line. See the trend here? We're getting closer and closer and closer to the set point. Of course, this PID algorithm is good for slow processes. This type of process. If you're working with a mechanical arm that is moving very, very fast, then this may not be a good algorithm, an ideal algorithm. So this type of process is slower than, say, a mechanical arm that is moving very fast and doing fast tasks. And so this would be, PID is a good algorithm for this type of system that is slower that is relative to, say, a mechanical arm that is moving very fast. So we have reached set point, or we're at least very close to it, and so these values work very well. So if you had this type of setup and you don't change the setup, then these would be the initial values you want to work with. So next time, so if you turn off the system and turn it on again, then you should keep note of these values. 3 for the gain, for the proportional control, TI 10 seconds, and TD 3 seconds. So these are the values you want to work with. So next time I turn on the system and I have the exact same, I don't change anything here, including the valves opening here and the pumping action. I don't change the pumping action. So I keep my system as much as possible the same thing. Then these values would be my initial values that I can work with. So instead of going again, doing the process that I did, which is time consuming, then you can start with these values and fine tune your system. Sometimes it may not work. Sometimes you're going to have to go through the entire process again. This is the flow chart here again. You're going to have to go through it again in order to get the proper values, or the initial values if you like, and then fine tune it from there. So I am here at the stage of fine tuning it, but other than what I have done, this is actually okay. I'm pretty satisfied with my control system. It is stable. I'm very close to the set point, and so this is good enough for what I have done here.